So, Professor, welcome to WOM, and thank you for your nice presentation that you gave to us, and also for agreeing to this interview. Professor Faist, your contributions to quantum optics and semiconductor physics, like particularly the development of quantum cascade lasers, have profound impact. You are also the recipient of several prestigious awards, including the Julius Springer Award for Applied Physics in 2019. And your works spans from fundamental physics to application-based. But every journey has its beginning, right? Mm-hmm. We would like to know what inspired you to pursue a career in physics, and how did you found yourself coming in quantum physics?
In my case, okay, let's clear. My father was a physicist. That's why, of course, as a teenager, the first thing I said is I don't want to be a physicist, because you, of course, don't want to do what your father is doing. And then I realized, okay, yeah, if I'm honest with myself, that's the one thing I seem to be a bit doing better than the other things. But of course, it sort of came as, I think as for many of us, you sort of like certain things when you're young, and playing with Legos, like many of us did. In a sense, there are two things which really got me fascinated when I was a youngster. One was electronics. So because electronics, you have your soldering iron, you can do stuff, and you can try, and then you burn your circuit, you're unhappy, and then you learn that you have to be careful. And the other thing was I sort of fascinated by sailboats, and I was building model sailboats. And then, of course, the question is, you try to optimize them to be fast enough. So in a sense, those were the two things that really got me very excited. That is, in a sense, you won't say for my more, I would say, engineer side. At the same time, it's clear that there was one thing which, at school, I got a revelation was geometrical, the geometry, Euclidean geometry, the fact that you can have a theorem. And that I found it fascinating, that you can prove something, and that was a revelation for me also. So in a sense, it really, in the end, came to those two things. On one hand, I always say that I'm kind of half an engineer, half a physicist, because in a way there is an aspect of myself where I really like building things that work in the end and that can be used. But at the same time, I really like this fundamental aspect, understanding deeply why those things work, where does it come back to this kind of basic questions. And so in the end, I can see that in the end, I was lucky that in the end I could sort of get those two things together, but it was not always obvious that it would work.
And how do you chose quantum optics?
I don't know to which extent it played a role or not, but when I was 7 or 8, my father was not really speaking too much about his job. So it was his job, so he was not really talking about it too much. But I could follow him, and he showed me his laser. I was like, wow, this is great. And then, as I said, I was sort of playing a lot with his electronics. And then when in EPFL, where I was doing my studies, I was looking for PhD position. There was this professor, my advisor, Franz Karl Reinhardt, he was doing optoelectronics. And I thought, oh, that's nice, because it has the electronics on one side and kind of the optics on the other. And I really liked that idea. And at the time, when I was studying, I remember we had the visit of Rodney Loudon, the author of the famous quantum optics book. He gave a few set of seminars, and he talked about squeeze states. And then I was like, wow, that's just amazing. I love that idea. But it's those things at the time I could not work on them because the topic was not really lending itself to it. But I really liked the idea. So in the sense, those were kind of the elements.
So you are very much you have pioneered quantum cascade lasers. So can you share us the story behind the invention and what makes it different from the previous laser paradigm?
Yeah. So, this is of course it's a nice story because it was something that was absolutely not clear it would work, and also was about to quit physics at the time. Because I did a first postdoc in Zurich in the IBM Röschliken lab, and there I worked on this quantum hole and had done my PhD in optoelectronics, and that was actually, in the end, you might say, as a career path was a bit of a, disputable decision. I was not thinking too much at the time. I thought, let me do something else. That's cool. I like this idea. But it was very good in the end because it taught me another aspect that I didn't know afterwards. And then when I apply through IBM, I was looking for a job, and then I heard that Federico Capasso was looking for someone, and he was definitely looking for someone to develop an intersuband laser. And there, I vividly remember our interview, and of course the fact that I had done both the optics and the transport then became kind of a very positive aspect. And I remember he said, well, this is I have this project. He was not really very clear how we would do it, but he said, well, no one tried hard. And that really resonated with me because I said, well, that's a very good argument. You need to, those things, you need to try hard, and I was absolutely ready to try hard. But even though at the time and for the first year and a half, we're definitely trying the wrong way. And the idea was, of course, what people were thinking at the time, which was, you take a 3-level system, you try to optically pump it, and then you use the fact that 2 levels are closer, and if they are closer than the phonon energy, then you hope that lifetime is long, and therefore you can maintain an inversion, and then you would have an optically pumped laser, because everyone knows it's easier to make an optically pumped laser than an electrically pumped one. That was, of course, the understanding of the time, but it was, of course, completely wrong. I mean, the optically pumped intersuband laser was much more difficult to do than the electrical one. Sort of, despite the good advice I was given to publish papers and find something else, I sort of stuck on trying to do this laser, even though the time was running out, and trying with a completely different approach, which was electrical pumping in the minute thread. And in a sense, I had accumulated the tools during those 2 years, and it worked out. It worked out also because I did a measurement of the lifetime. For a laser, you have 2 important aspects. You need to know how much gain you have from the transition, and that, thanks to the work also of my colleague Carlos Sirtori, we understood that you could predict it well. The next point is how many electrons can you hold on there, and that is the lifetime. And the lifetime, of course, our model was saying initially the optically pumped laser should have lased, and it did not lase. So what is going on? And that's when, and said, okay, maybe we don't understand the lifetime. And then made another experiment, understood the lifetime, programmed it in a code, and then you can, if you have the code and you trust the numbers, you can start designing things. And that's basically how we got to the quantum cascade laser.
It's very interesting. Yeah. Could you tell us if there are any fundamental limits to quantum cascade lasers, and do you see room for further improvements?
The limits are mostly the material. What limits the quantum cascade laser is the quality of the interface between quantum wells, because that's a major limitation as you're trying to make the quantum wells thinner. And so it is a limitation, for example, when you try to make larger and larger photon energies, because there you need larger and larger transitions. And first of all, you're limited by the finite discontinuity in the conduction band or valence band of your materials. And then, of course, also any roughness of the interface plays a more important role. I think we tried really hard in these 20, 30 years of doing what we can do with engineering to overcome those limitations. Of course, if one could control, again, the fabrication technique, if you could do a quantum cascade laser based on quantum dots, that would be amazing, of course, but the technology is not there. It remains a very interesting device, and the quantum walk laser that we just quantum walk comb that we just came up with is again an example of showing it's something that is more general than a quantum cascade laser, but in a sense you could see it so well because the quantum cascade laser has this amazing feature of where you engineer and understand the lifetimes and the transport. So it's kind of a very organized system, and so that allows you to go further even in fields that are not directly quantum cascade laser based, if you want.
And in what emerging areas can quantum cascade lasers can be used?
One very important feature would be to be able to make very small ones. Mm-hmm. Very small quantum cascade lasers that retain a good efficiency of a few percent, because those you could put in many portable systems to do sensing. And that's one thing that I have a postdoc is working and trying to do it, and I'm sure he's not the only one. But that's one of the things that I would say, in terms of the application, would have a huge impact.
So today in your presentation, you talked about vacuum fluctuations and to control and tailor solid state phenomenon using it. Can you explain what is vacuum state and what are vacuum fluctuations and how do they influence atomic and solid state physics?
I mean, what is fascinating about those vacuum fluctuations is they are really the expression of quantum mechanics, really in the deep way. It means quantum mechanics tells you in the end, if I take a pendulum and I try to stop it, I cannot really fully stop it because it will always have this fluctuation in position and momentum. And so it's exactly the same thing with the electromagnetic field. The electromagnetic field, you can try to make it as small as possible by lowering the temperature and turning off all sources, but then there's still this thing that stays. And that fluctuation is there, was really something that was extremely conceptually important. Already when of course the lamp shift was measured, it was a revolution because people realized I cannot just think of the atom as an isolated thing and separate the radiation. I mean, the radiation and the matter are kind of the same thing, if you want. They are connected. And really what we're trying to do with this vacuum fluctuation controlling solid state matter is, of course, expand that idea to now some solid state system and try to see that it's a complete field where people have not really thought too much about, because of course for a number of cases it simply doesn't do anything, but there are cases where it actually could really induce something, and that's of course quite exciting. Also because in the end, if you think about quantum computers, you try to minimize all sorts of noise, and then vacuum fluctuations are always there, And so that's something that might also play a large role in that type of application.
So using this quantum fluctuations, you could able to break the quantization of quantum Hall effect. So why is this important?
I think there are two aspects to it. One is, of course, whenever the quantum Hall is, of course, very important because the quantum Hall is also our standard of resistance for the SI units. It's a secondary standard. And I think when you build a set of units, and you need to understand what the limitations are. And it's, of course, so far people have claimed, or with good reasons also, with theoretical reasons, that these limitations of the quantum Hall are understood. Now it is still interesting to understand, have they really thought about everything, and aren't they a possible correction due to the vacuum fluctuations? After all, the corrections of the 1s-2s transition of the hydrogen atom was 1 gigahertz. I remember, talking to experts in the quantum Hall who were actually interested in saying, well, it's not totally clear that there's no so-called radiative corrections to the quantum Hall, because a number of other fundamental phenomena have radiative corrections. So in that sense, I think there's a fundamental interest in seeing to which extent to understand better, let's say, the limitations that are perhaps coming from connection to the vacuum fluctuation. But at the same time, we've shown that you can actually also do positive things like controlling stripes and induce states that would not appear otherwise. And when we control the stripes, we are doing it in a unique way, which is better than any other way that has been shown so far. So it's there, the vacuum fluctuation is doing something that you cannot do with anything, at least as good with any other way. So I find it really nice. It's of course to push this vacuum fluctuation as being kind of just a source of annoyance into something that allows you to build new states in a way that you could not do before.
Your research work also involves strong light matter coupling, right? how hard or like difficult is it to achieve this regime?
It's a good question, because in a way, there are now, I think, researchers that have shown that there are very, I don't want to say simple systems, but in a way, systems that are not so complicated to achieve that regime. And in the end, it's really, you take a very strong optical transition, put it, you couple it to a resonator, and that's it. You can have this collective excitation, which has this very high, very, very strong light matter coupling. So I think that's why the next important question is, yes, and what do you do with it? That's where I think then, that's why we're going in that direction, if you want.
So, like in recent times, there have been many researches going on in quantum optics, semiconductor physics. So like, what do you think, like, where do you see, like, in the next 10 years, do you think like this field will be evolving?
I think the field, of course, there is this very strong work done on all these 2D materials, which is absolutely fascinating, of course. There, the challenge, I think, is to see how can we translate, those fantastic samples done with Scotch tape to something that is produced, more in an industrial form. And I think quantum optics is going to stay. It's just too amazing. You can do things which are too cool. Yeah. And I think part of it is also because in the end, what we should never forget is that how do you get to the quantum? It's by making the classical so good. You see, what makes something quantum is usually when you can remove all the dissipation terms that were kind of classical. So if you think, why are, let's say, the optics at 1550 so rich? Well, because you can make those fibers that have basically no loss, and you can interact photons for so long. We can make now circuits on silicon photonics that have this amazing low loss. And so I see that there is really a lot of things that can be done because of that.
And in research particularly, like not only I think like individual expertise, also like effective collaboration and leadership also matters, right? And since you yourself run such a big group, what do you think, like leadership like has made you more, like evolved you in your research? Or like, do you find that, it challenges you in some way?
Of course, in a way, I always tell that the most beautiful aspect of our job as professors is really that you see PhD students evolve and grow up scientifically, and that's extremely rewarding. And of course, it's, if you want the best, for me, it's the best part of our job, is to try to, help those people get their scientific persona and maturity and evolve in their direction. And I think leadership is immensely important. We cannot sort of say how much it's important that as a community we live by our values truly, and that means definitely, making sure that you sort of that you really try to be honest with what you do and promote also the younger people. I think that's fundamental, and it's I've had really a lot of examples personally when I was a younger scientist of people who helped me or sort of really were at some key aspect of my career. They really sort of made sure that I could do what I wanted to do, or pushed me in the right direction, and that was of course extremely important for me.
You see, like research is expensive, right? Like to do the things that people are doing, it takes money and also like time and patience. But in recent times we have seen like there are like cut down in research funds by countries or due to many reasons. Like, how do we motivate people or like the leaders and people in general, so that like, because research is important for the growth of humanity, right? So what do you have to say about this?
This is a very good question. And I think, of course I have this faith that in a sense it's one of those activities that make you a human, in a way, because it's really about, understanding, about making a model and understanding reality and using that in a positive way. And so it is clearly associated with kind of with culture and as what makes a society worthwhile in a sense. And so I think it's important that we, of course, emphasize how research brings, if you want, something to humanity in practical ways, but I think we should not limit ourselves to that. I think the intellectual aspect and the fact that it helps us being a better society in general, I think also should be emphasized. And that's why also it's so important that as researchers we behave ethically, because I think that's where the added value is also for society.
Thank you, Professor, for your time and everything. This was really nice talking to you. Yeah.